processors, but by interviewing the engineers who built the processors about what they had in mind. And so our hope in DeepSpec is to leverage some of this work at the University of Cambridge and elsewhere to get instruction set architecture specifications that are fully formal and that we can actually believe. Other questions? Yes?
Well, a lot of this project and the presentation was about functional correctness. You mentioned some aspects of resources, but has there been any effort to verify, for example, maximum memory usage of a particular program?
Right. So the question is...
resources more generally.
Right. So the question is, I've talked a lot about verifying functional correctness, but what about verifying resource bounds of programs? And the answer is yes, especially at Yale in the Certicos project. They've paid a lot of attention to verifying resource bounds. And it's on our list of things to do in the verified software toolchain, where the separation logic naturally permits specification of some kinds of resources in both time and space. And it should be possible to do that reasoning in the same verification where you do the functional correctness. Yes?
You showed the distinction between in the table specification on one side, and that when this table specification is good enough, fast enough, then it's good because we don't have to make this refinement step and put it correct. But when it is insufficient, then it's possible to go to a C refinement and put it correct to this original specification. But those are two extremes in the sense that for the specification, the set is completely absent, and for the C specification, there is a huge burden for the proof of refinement. What about the space in between? Imagine that just a little bit more control over the representation than for the specification, but not the whole power that C gives us.
Right. So the question is, I talked about verifying a functional program and then using a proved correct compiler to compile it and run it in a garbage collected way. And when that's efficient enough, that's a very good way of doing verification. And then the other extreme, which is to implement a C program and prove that it refines some functional program. And that's a laborious verification task, but it gets you a high degree of efficiency in the C program if the C engineer knows what he or she is doing. But the question is there something in the middle that is less work than writing the C program and refining it, but more efficient than a pure functional program? And surely there must be. And what would be in the middle? It would be, in a sense, a programming language design for some sort of programming language that might lead to more efficiency than a garbage collected functional program, but more reasonability than C programming. And one example of a language that might fit that criterion is Rust. And there's active work on building a proof theory for Rust and a semantics for Rust, for which it'll be interesting to watch. Yes?
So my understanding is that as a client of Concert, you basically heard that Concert moved towards a small step semantics for their semantic preservation proofs. And one of the reasons for this was to facilitate reasoning about concurrent programs. So my question is Concert's semantic preservation proof in a state where you're quite satisfied that you can do the kinds of proofs about concurrent programs that you wanted to do, and are you making use of these?
So the question is the specification of CompCert, to which it is proved correct, strong enough to reason about shared memory concurrent programs compiled by CompCert? And the answer is, in the standard version of CompCert as distributed in the master branch, not quite. And in our version of CompCert, Yes. So one of the research projects that I didn't talk about at Princeton is a slightly different specification of the CompCert verified C compiler, a minor adjustment of the proof of CompCert so that we demonstrate it's correct with respect to this stronger specification, and then a proof in Coq that from this stronger specification you can derive the correctness of execution of shared memory parallel programs synchronized by semaphores running on machines with weakly consistent cache models. And we have a paper on that submitted for publication. Other questions? Yes?
Is there any work on formalization of I/O, like PCI versus SCSI?
I'm sorry, formalization of?
Input-output, like SCSI.
Oh, formalization of input-output. Yes, absolutely. That's actually very important in, for example, the deep spec web server, which if it didn't do any I/O, you wouldn't be able to tell it was there. So in the very end of this summer school, in the 2 lectures about the deep spec web server specification and verification, you'll see how we specify and verify I/O. Yes?
So this certain cost verification assumes the correctness of the machine state or those components that are managed by processor and operating system together?
Right, so the Certicost verification, what does it assume about the correctness of the machine state? So I'm not sure what you mean by the question, but I'll answer 2 different questions. One thing we observe about the SEL4 verification, which is a great pioneering effort, but there's no proof about the initialization phase of the operating system up to the point where it starts running. That the initialization phase is not proved correct, but then we can make an assumption about the state after initialization, and the correctness of the ongoing execution of the operating system is proved from there. In Certicos, even the initialization phases are proved correct. So that's an answer to one question that you might have asked, but I'm not sure. The other question is, what does Certicos assume about the hardware and the program, the programming language, right? Certicos runs on some piece of hardware, whether it's x86-32, it also runs on x86-64, it also runs on ARM. And for each of those, we have to assume a certain formalization of the semantics of the instruction set architecture, which, as I described in my answer to the previous question, might be right, but who knows. Still, there's excellent work by researchers elsewhere in the world testing whether those are right. But for true end-to-end confidence, we're going to have Certicos running on the RISC-V connected to a verified implementation of RISC-V down to the transistors. Other questions? Yes?
So not every function in Haskell is total, while every function in code is total. So how do you match the not partial function and a partial function and total function?
Good question. One answer is monads. One answer is, and I'm not an expert on the HS2Coq tool, so this is sort of a guess, but you can do HS2Coq, and if you can then prove things about the Coq function, you might also prove that it's total. And so this works for verification of those Haskell functions that happen to be total. But that's an incomplete answer because, as I said, I'm not an expert on the HS2Coq tool. Other questions? Yes?
Yeah, I have a related question. So you presented a lot of different reasons why it's good to have functional specifications. However, for example, operational systems and web servers, I hope they are not total. And such that they stop after doing something, so they have to wait for something. How do you specify this?
Right. So the question is, how do you give a functional specification as a total function of a program that's supposed to keep running forever? Because the thing about a total function is that it does terminate. And the answer is you write functions that operate against a monadic interface. So each interaction with the monadic interface is a function that terminates, but the sequence of interactions can go on forever. And this will be presented in some detail next week in the lectures about the web server specification. Other questions? One more question. Last question.
What you just said, is that some alternative formulation, or is it completely different from some specification based on code data types, where we see, let's say, the operating system as a function from a stream of input to a stream of output, like an infinite stream of input to an infinite stream.
Right. So I think the specification model for interaction trees is similar and perhaps even isomorphic to some things that are already in the literature. And I'm not a complete expert on that either, so I plan to learn a lot from next week's lectures too. So we'll see you next week. Okay, so I think that's it for the deep spec overview. And for those of you that want to stick around, I have a second little lecture about some local history. Some people you may have heard of named Church and Turing and Gödel and von Neumann and Einstein and so on. So, thank you.